Hi all, thank you for coming to today's speaker series. We have a slight change in our speaker. Um, Today we have Mr. Tenmoy Sen, who's a UVA student who works with Dr. Hein Chen, and he's going to share with us this presentation titled Prototyping Data-Driven Cyber Attack Detection Techniques in Autonomous Vehicle Cyber Physical Systems. So thank you for your patience. And we're really excited to hear. So you can take it away.
Good morning, everyone. Thank you for being here. Sorry, Dr. Heinchen cannot be here. So I'm going to present our work on prototyping data-driven cyber attack detection techniques in autonomous vehicles, cyber physical system. As we all know, like many semi-autonomous vehicles are actually currently on the road today, and many states and cities has already deployed and about to be deployed autonomous vehicles. And these states and cities includes like Virginia, Arizona, Texas, California, Pittsburgh, Ohio, Detroit, and so on. And we also know that the autonomous vehicle market is currently booming, and it's actually considered to reach about like 200 billion by 2030, comparable to like 15 billion in starting from like 2021. And a part of like this autonomous vehicle concept is basically connected autonomous vehicle, where we consider like vehicles are communicating with each other, not with through like different kind of networks. And this network includes like different sort of like vehicle to everything kind of networks. It can be like vehicle to vehicle, vehicle to infrastructure, vehicle to pedestrian, so on. And based on this concept of autonomous, connected autonomous vehicles, United States, like transportation department has considered some kind of alert system based on this connected autonomous vehicles, where these vehicles based using like roadside units and through communication to each other can develop alert systems that can actually post some sort of crash notification, some speed limit advice, some lane change notifications, and so on. And as we have mentioned, this connected autonomous vehicle system like constitutes of like different sort of network technology. But the crucial part of this technology is is V2V. And as V2V network is mainly dependent on like different open net, like wireless network system, like sorts like such as WLAN and Bluetooth. And this has like communication with a mixture of like short range and kind of open network. This network is kind of vulnerable to different sort of like cybersecurity attack. So as the cybersecurity attack is more vulnerable in such V2V networks, like detecting such attack and handling them is like very crucial, as like in transport scenario, like some kind of misidentification can lead to like destruction of human life and like severe accidents. So so what we are trying to handle in this project is like how to handle the security threats in that arises through misidentification or like some message parsing introduced in the V2V scenario. So for example, here we can see like if in the V2V scenario, like some sort of like vehicles can, let's assume like vehicles can pass each other message in a CAV scenario where they can communicate with each other, like how are they going to respond next. So if I consider like the green vehicle is sending such or sort of like parked out message that is actually not true, it may lead to like accident in this route. So basically what we are trying to handle in this scenario is basically how to handle such sort of like false message sent by an attacker in the CAV. So let us first like introduce like the background, how this message system work. So in each vehicle, there is a like a bus, like so like a control area network bus. And basically what happens is like two vehicles can communicate with other with like a CAN message. And the problem here is like an attacker can itself like identify itself as a trustee, like trust of the user within a like a vehicle network and see send false messages, or it can be hacked by someone from outside, and the message sent by a vehicle can be modified so that the it can be is misidentified and lead to some sort of attack and like and cause some havoc in the road. So basically the concept we are targeting is like how if like a attacker modify the CAN message, and the CAN message is actually processed inside the vehicle in a unit, and then it actually takes the decision. And in the alerting system, actually US like Department of Transport has identified sort of like 30 safety critical like warnings that actually can be passed among the vehicles. So here we are actually targeting like 4 or 5 of those. I'll introduce those warnings in the upcoming slides. Like attack scenario we are introducing based on the warning is like a control loss warning. So basically consider like the VI, like the vehicle, the white car in the front is the attacker. So what it can do is like it can say, "Hmm, I am braking," but actually it's not. And its report its position in the red dotted mark. So what will happen is basically it will send this like like the braking scenario in to the other two vehicles, and it would cause the other two vehicles to slow down. And if you like a sudden change of like certain brake application or like control loss is sent, it can actually lead to some like accident to the following vehicles VJ and VK. So reported false location can be a form of like attack that can happen in the CAV scenario. Next form of attack, which what we are like trying to formulate is like false stationary vehicle warning. So what may happen is like it's not only like for stationary vehicle, or it may say like there are like some accident ahead or some sort of like road blockage, this sort of stuff. And an attacker vehicle can report like false accident saying, yeah, there is a some sort of load like mm, like accident ahead and road blockage ahead, and it notifies like the other vehicles that you should take a detour because of the blockage. So it can actually like force a specific vehicle to take a detour and cause different sort of harm. So this is another attack scenario that can happen. The next attack scenario can be like a false lane change warning. In this attack scenario, what may happen is the vehicle VI is trying to change lane, and the distance between and it has doesn't have like enough space to like change the lane. So what it can do is like say to the vehicle VJ is like, I want to change the lane and my position is like this. So it would force the vehicle VJ to like slow down suddenly and to increase the space. And basically it can lead to like a accident and many other scenarios. And the final scenario is like the like the fall not the next scenario is like the fall emergency vehicle alert. So it basically like notifies the preceding vehicles like there is an emergency vehicle in the lane, you may need to slow down. So basically it slows down the vehicle, and the attacker vehicle can gain some like advantage by sending some um, such false alert by speeding up and do some like cause some like accident in the road. And the final scenario we are considering is the false blind spot warning. So in this scenario, it's kind of the same as the first one. So here the attacker vehicle is notifying is like mm, location like falsely and forcing the vehicle VJ to like slow down and let it pass. So this can like sudden slowdown and sudden lane change or sudden false information can lead to like different sort of accidents and and also like different sort of like havoc scenario to the user itself. So by keeping this in mind, we are actually proposing an attack detection on vehicle driving signals. And we are specifically targeting the vehicle to vehicle communication system to where the exchange of driving signals are happening. So in this scenario, what we are considering like a sender vehicle, multiple sender vehicles are sending signals to the recipient vehicle, and the recipient vehicle actually conducts certain machine learning based computation and decide like whether the received signals is actually the uh, expected scenario based on the received signal it has until now, and it tries to predict whether the next signal is same as the received signal at that moment and decide whether the current received signal is actually an attack or not. So if I detail the possible method of attack detection of the current prototype we have, so what we consider here is like each vehicle has some sort of like V2V component, and say like one vehicle A actually collects time series signals data with like n features t time steps and send it to the other vehicle V. And the time series signals we are considering currently is basically the steering wheel signals, brake, acceleration, and velocity. And when a vehicle V receives the signal data from the vehicle A, it forms a network of a window of like the previous signal. It's kind of like a sliding window. And then the vehicle B uses a like machine learning model to make the prediction of the future signal data. So it basically takes like the k time steps of all signals like as a window, and it predicts the next signal what it should be. And then it compares like based on the prediction whether the predicted data and the received data are similar. If it's not, we detect it as an attack. Otherwise, it's a good data and we can proceed. So based on this method, we developed a prototype using like the Coda wireless devices. These are like a emulated version of the RSU, like roadside units. And we use this alongside with like many other devices. We have like many Raspberry Pis, Spark Edge, Arduino, and maybe many wireless like mobile devices that we can use. So basically what we do is like we use an Arduino device to collect data, and here from the canvas, and the canvas is basically sending like a okay information that is like a normal mode, and we can collect the data right now through the Arduino. And the Arduino collected data is basically a control code followed by like 8 bytes of data. And this 8 bytes of data actually consists of like different sort of signals, including brake, steering wheel, accelerator, velocity, and this sort of information. And this collected data like is this data is collected like until the a vehicle is moving. And to create the communication network, we actually relies on the wireless mobile devices. So basically, we are sending the received data from Canvas to a mobile device through like Wi-Fi direct. And then we like send this, we developed an app between two mobile devices two vehicles, and the sender device can send the data to a receiver through that app. So basically what we can see here is like that the data sent by the sender is like received by the receiver. And then the receiver device can do certain computation and run a machine learning model to predict like the next signal, what is happening. And based on that, we can decide whether it's an attack or not. So currently there are two options, like as we are considering the V2V option. So it's actually done in like a small computer, like laptop in the car, like installed in the car itself. But basically what we'll do is like have a device installed within the car in the future where it can do the computation. So basically the processing is like at time step T, a input signals for like time window 1, and we are actually predicting using a LSTM based model what should be the signal based on the previous window at that time step, and we continue to do so and do the comparison to detect the attack. Yeah, so basically the computation is done with the vehicle itself using the like a edge device. Here is we are considering a small laptop with a just like limited resource to do the computation and do the prediction itself. So we did some sort of experimental evaluation of our prototype, and we actually chose a LSTM based model named MLSTM FCN that we can see in the picture. So it has a like a parallel LSTM and a fully convolutional network that can see the data, time series data, both as a univariate and multivariate at the same time. And it tries to classify whether uh, the received signal is an attack or not. It's basically a classifier-based model to directly detect whether the received signal is from an attacker or not. So basically, for the input signals, we consider the brake, velocity, acceleration, and the steering wheel angle. And for for this prototype version, we actually chose like different maneuver classification, and we categorize them into like 4 classes, and they're like maintaining speed, stopping, left turn, and right turn. And we launched some time series based attacks that actually try to like misidentify these like maneuvers to like different maneuvers in untargeted form. And we use like two like well-known time series based attacks that are available in the state of the art, that they are like zoo and auto zoom. So in this method they try to like insert some sort of perturbation within the signal that is actually misidentifiable by the human eye, but but still like it can confuse the vehicle itself to take some wrong decision. So these two attacks we actually launch, and we try to run our MLSTM model to detect whether they can identify these attacks. And as an experimental metric, we chose like these 4 metrics: the accuracy, precision, recall, and the detection time is quite important, because in the vehicles, like in the transport scenario, many of the decisions needs to be taken in real time. So the detection time should be lower. So from what we observe is basically our MLSTM FCN model can detect the zoo attack with like around 92% accuracy, and the auto zoom attack with 90% accuracy, with like satisfiable amount of like the recall and the precision. And the detection time for the zoo is around 240 millisecond, for uh, auto zoom is around 310 millisecond. So we will try to like reduce the detection time more, because it actually needs to be very real time in the transport scenario. So currently we have like a current working prototype running. So we actually plan to collaborate with our um, like industry collaborators, the IBM and the Peron Robotics. We want to collaborate with them in like developing, deploying, and disseminating and preparing the for commercialization of the software project. And we can actually use their software stack and add our prototype, the machine learning model as a component so that it can be used and tested in a industry environment. And if we consider the impact of our project, it can have like manifold impact. First, comes the commercialization. So we want to commercialize our project as a like a software and also and also provide the hardware if necessary. For the commercialization, we actually want to adopt and distill our research results into real world products. And for doing so, we want to address the commercial issues towards the initial stage of the technology development. So, like in this phase, we want to concurrently gather information about markets, potential customers, the competitors around the market, make some strategic direction, what direction we should follow, and what financial decision we needs to make it a viable commercial product. And this, if its prototype is made commercialized, it will help like have some economic impact also. So it will show some growth on the on entrepreneurial ecosystem in the Commonwealth. And if it is launched at like a wide scale product, it can ultimately create some job opportunities for the advancement and the development of this product. And we already know like around 2017, around $3 billion were used for the crash related accident in the Commonwealth itself. So this product, if we can move to like a CAV scenario, this product can actually help in reduction of the estimated cost related to crashes. And finally, it can actually help to like in developing the workforce because like we are many PhD students and undergraduate students working in there. And throughout this project, we are expected to like spawn a generation of professionals like researchers, designers, and developers who are actually well equipped with the foundation of the cybersecurity in the autonomous systems and CPS. So in conclusion, due to like CV's connection and the external networks like WLAN, Bluetooth, they are like vulnerable to attacks. And in this prototype, we are trying to like develop an effective diffraction technique that is crucial for like the CAV safety. And in the current prototype, if we can commercialize it like properly, we can create like a appropriate metric that can help mitigate these risks and safeguard people from different kind of accident scenario that may rise from these attacks. And we can have like some commercial and economic impact in the Commonwealth also. So we have been like many PhD students and undergraduate students working in this project. The project is led by the Dr. Haing Shen. We have been working her guidance for like around 1 year or so. And thank you. So do you have any questions or comments?
Thank you for this presentation and thank you for coming out. We really appreciate it. Um, be sure to join us next week for our next installment of our speaker series. Thank you, everyone. Have a good one.